Thank you very much. Hello, and thank you for coming. And thank you, Daniel, and LifeRay, all the people from LifeRay for organizing this meetup. I'm very happy to be here to talk about Coq and Haskell, of course. So let me take some time to explain what Coq is all about and what about its community ecosystem, how it's kind of organized. Then I will tell you about some theoretical underpinnings of it, and then we will talk about connections between Coq and Haskell, what tooling there exists. Okay, so it's a formal proof management system, right? So I will try to kind of explain and decipher many of these words, right, along the talk. So at first, it's a language. It's a functional programming language to write some mathematical definitions, some functions that compute. It's a total language, which I will be talking about a bit later. Okay, so you can write theorems or specifications. You can totally express everything you want about your system because of its expressive type system. And also, it's an interactive system, like it has an environment for interactive developing, and as my coworkers say, it's actually not possible to develop anything in just plain text editor. You need an environment which would guide you and help you, because it's just too much context to keep in your head when you do proofs. So that project was started in RIA like 35 years ago, around that time. So it evolved. Now it's Coq 8.8, the version. So where it is placed in the broader context, right? So it's the land of formal methods includes such things like specification languages, such as TLA, for example. Maybe people have heard about that. Or interactive theory improvers, such as Coq itself, or the lean theory improver, or Idris, or Agda. It's SAT, SMT solvers, some kind of like automatic solvers, right? So, for example, in Coq you have to interact with computer, but you are writing your proof by hand, sort of. There are things which actually allow you to prove automatically stuff, right? You just write your statement, hit the button, and they prove some. For example, such tool like Liquid Haskell relies on that. And some people would even argue that if it can be proved by automation, that it's not really interesting. Like, if you don't have to think about it, it's not interesting. Okay, so then there is model checking. It's more about automatas, so it's not that expressive, but it can do its job. Then there is program logics, such as HOR logics, for example. Some stuff like separation logic, which we do at MDS Software. It's the institute where I work as a research programmer. So I'm doing Coq on daily basis. Now, related systems, right? So the lean prover that I mentioned, it's very similar to Coq, written in C++. So now it's in its 4th version. With the version 3, I got some segmentation faults, which is fine, C++. No offense. Okay, now Agda. It's non-predicative system. This is kind of like goes outside of the scope of this talk, predicativity versus impredicativity. This one is developed in Sweden. Then there is Idris. It's developed in UK. It's a system very similar to Agda. They started kind of at the same time, and the thing is, Edwin Brady, the guy who is like the main author of Idris, said in one of his podcasts, like, if I knew that Agda existed at that point, I wouldn't bother to implement Idris. But now Idris is a dependently typed programming language, like general purpose programming language, which is really cool to actually see that these dependently typed systems, they come to the general practitioner, like to the working programmer. There is F-star, kind of lots of hype I hear about it right now. So it's code generated from F-star. It has been accepted into Firefox, right? I see Firefox here on the t-shirt. Okay, so it's verified, so it's mathematically proven to be correct, and that's very good. Then there is Isabelle Hall. Hall stands for higher order logic. It's a system very, very different from Coq. So at first it's not a constructive system. I will try to explain what that means. It's based on classical logic as opposed to constructive one. And also it has very good tooling around it and very good automation. There is a tool called Hammer. You can nail your proofs down with it. Okay, there is a project, very cool one, SEL4. It's a project. It's a verified embedded operating system. It's already been used in the wild, right? But it's kind of special thing. So military guys love that. So what do we use Coq for? So there are many uses. We will be concentrating here on more how it can be useful to the programmer, right? So, but let me mention some of the uses which are maybe not that interesting to the programmer, right? So you cannot really use it in practice, I guess. So it's been used to prove the four-color theorem, very famous theorem, very controversial theorem, because it was proved in the 1970s by Kenneth Appel and his co-workers, and they used computers to do that. So they wrote a computer program to actually go through different variants and options, you know, and try stuff. And then mathematicians of that time, they were like, come on, it doesn't make any sense. Like, what if your program contains a mistake? So it's not a real proof. So they were really, really opposed to that proof. But now, like 30 years later, some people, led by Georges Gontier, they proved it using Coq. So they built a very big library for that. That was the beginning of the MathComp library, which I will mention again a bit later. So then there is this Fay-Thompson theorem, or the odd order theorem. It's about finite groups. It's like core mathematics stuff, maybe not very interesting. But it was a huge effort. It's probably 10, 20 people working on this for 8 years, probably, like full time at the universities, at different universities, right? So this is fully formalized. So everything is proved. Then maybe you have heard about this homotopy type theory, which is really popular these days among people who are into type theories. It was also built using the Coq theorem prover, and Vladimir Voevodsky, who is the originator of this homotopy type theory, when some people discovered mistakes in his earlier works, he was okay, so what do I do? Because the proofs in mathematics, they became basically unmanageable. So there are ongoing efforts, like many books of proofs. And in the whole world, like there are 2-3 people who can actually check those, and it's very hard to do it by hand. That's why you would need a computer to do that, right? It's called a proof assistant for a reason. So in education, you can use this kind of thing in education. For example, maybe those of you who went to the university and they took like calculus, for example, right? Calculus proofs, like what do I do? How do I check if my proof is correct or not? Like what's that? Like you give your papers to the professor, right? To the teacher, they return it to you like with all this mistake, here's mistake, like there's logical inconsistency, whatnot. With this kind of technology, it won't be possible. If it's checked by the computer, done. I mean, I totally trust the computer more than a person to go all over my proofs and check those. Of course, yeah, there is a possibility that there is some kind of bug in the Coq proof assistant, and of course there are bugs. Like there are how many issues they have on GitHub? In the thousands, I guess. But most of them are just minor things. I mean, some glitches in the user interface or stuff like that. But there is this kernel, the part in Coq which you have to trust, and it has to be a very small piece of software which can be checked by many people, many experts in the field, and if they say, yeah, okay, we can trust that, then probably you're okay. So I would trust those guys than just random people. Okay, now let's go to the meat. Okay, so this is the Deep Spec project. It's a project which aims to combine all the good stuff about formal methods around Coq. And so let me actually go and highlight some parts of it. Of course, we don't have time to cover the whole project, and it's an ongoing effort, so it's not finished yet. Okay, let me check if does this work. But I cannot really see it. Okay. All right, so let me show you, for example, this part, which is called CompCert, this part in the middle. So CompCert by Xavier Leroy is a certified C compiler. So it's basically written in Coq. It has lots of theorems. It's proven correct. Of course, people found bugs in it using some kind of fuzzy testing, for example, but they found bugs only in the non-verified parts. We will talk about that later as well. Now, then there is concurrent verifiable C, so there is a system on top of it, so you can interface those, which allows you to write programs in C, then write statements about those programs, like Hoare logic style, and prove them correct. Then this system would extract everything to C. C would compile with this certified compiler into assembler. Okay, then there is ongoing effort with this blue spec compiler, so people are trying to actually certify it as like the whole stack. So from hardware up, and until SQL, right? So SQL is going to be covered as well. So lots of companies and research institutes are into that, so there are some branches that are go through LLVM, let's say, into Haskell. We will talk about some parts of it a bit later as well. There is a project called Certicos, which is like aiming at the same market share as SEL4, the Certified Operating System. So yeah, that's it. It's a very big world. Lots of people are working on this, and some of these we will be covering a bit later. So more examples. So Coq generated code is already, you probably already used it. If you use Chrome browser, you were using some code, some C, C++ code, which was generated from Coq. It's a project by Adam Chipala. It's in Coq world, he's very famous. He does very, very cool things with automation. So he's like the LTAC hacker. There is this language called LTAC, which our group doesn't really use, so I cannot claim that I'm an expert in that language, but what he does is really, really impressive. Now, there is a file system, verified, written and verified in Coq. Some people also claim that they found bugs in it. And the authors acknowledge that, yes, there are bugs in it, but in non-verified parts, exactly. Yes, again. Okay, so then there are, okay, let me catch the hype wave, cryptocurrencies. So I myself actually started with Tezos. We were developing, formalizing their Michelson language for smart contracts. Then I abandoned this project and joined Alex Znanievsky team to come here and work with Coq in Madrid. So I wasn't the guy at the end of the project, and I guess it ended up in a state where they changed the language, and then people started to jump off the ship. It's not very pleasant when you constantly changing the system. You have to have your language kind of like stabilized, then you can formulate and formalize claims about it, because it's hard to claim something about something that is not really stable. It's today it's this, okay, tomorrow it's some other thing, and it's kind of hard to do proofs. It's very satisfying, but also time-consuming at the same time. Okay, there is this company Zilika, I don't know how to pronounce it. So they also use Coq for formalization of the smart contracts, right? So like you can have lemmas about your contracts, right? Like a contract will have enough funds to refund, for example. It's a statement. It's a logical statement. You can formalize it. You can prove it correct. You can definitely prove that everything works as it is expected, and it's very, very important in this fintech sector, right? It's a project by Ilya Sergey, by the way. Now that one. So now let's. We already have seen that Coq has some applications in real world. In research, it started as a research project. So of course, I think most of the Coq users are researchers of some sorts. But there are people in industry who appreciate and support this kind of effort. So Coq is open source, right? So it's like 35 years old, around that. It's on GitHub. You can go there. You can clone it. You can make your changes. Do a pull request. Maybe you will get your code in this code base. That would be really cool, especially if you would manage to get it into the kernel. And some people actually did that, like outsiders, especially if you're an expert in OCaml. So it's written in OCaml. It has a standard library, pretty extensive one, but I would say it needs some kind of it needs a revamp. You need to reorganize things, polish them a bit. It's a bit hard to use it as of now. Now, how familiar people are here with the OCaml ecosystem? So, for example, OPAM. So, did anyone use OPAM once? Cool. Okay. Okay. So we have one OPAM user. So, if you use some kind of package manager like apt, I don't know, homebrew, whatever, it's a lot like this, but it's source-based, right? So you clone it clones it for you, compiles it, and installs, right? So lots of packages are available. You can install Coq using it. You can install OCaml. Of course, you need some kind of system OCaml compiler, or your package manager, right? So you type sudo apt install opam, right? Then it will get some dependencies. You will say something like opam install Coq. That's all. But the thing is, opam doesn't really work good on Windows. So if you are on a Unix-like operating system, like some flavor of Linux or macOS, you're fine. But otherwise, it's also there is a. So what's his name? Sorry. His name is Michael. I forgot his last name. Sorry. He's from Germany. He works at Intel, and he's really, really concerned about Windows. And so he makes all these packages for Windows. So maybe these days it's better. You can just go there, go on GitHub to the release page, and download the whole package with lots of additional plugins, whatnot. Okay, so there is a community-driven project, Coq community. So if you will decide after this talk that okay, maybe I want to try Coq, you will decide that at last you would like to stick to it, then feel free to join. You can discuss. People are generally friendly there. Okay, some stats about different Coq projects. So let's start with Coq itself, right? It's around 200 lines of OCaml. OCaml is a programming language. It's a functional programming language with elements of imperative programming. It has references and whatnot. So it's not like Haskell. So if Haskell people want to insult OCaml programmers, they just say, "Oh, but that's an imperative programming." Okay, now you have around 200 lines Coq code. It's mostly standard library, which comes with this package. Of course, you would have tag, markdown, some documentation, right? Now, what else? There is a library called mathcomp. It's a library that has been used to prove the Fay-Thompson theorem. It's the library that I enjoy programming in every day. It's way smarter than me. Especially the guys together collectively who designed it. It's one of the best designed pieces of software I've ever seen. Yeah, it has 300 lines, 1,000 lines of HTML. Of course, this is not real code. It's basically they extract documentation from sources. So there is this tool called CoqDoc. It's like all those tools like Haddock, right? There is. Okay, so it's a pretty big and impressive project. They did a good job to not turn it into a bloatware, right? So it's all right about FCSL. So FSCQ, sorry. It's a project aimed at formalizing and writing a file system in Coq. So you can write a file system which is then proven mathematically to be correct. And so some guys using a tool called Crash Monkey, they crashed it, and it turns out that even verified file systems have unverified parts. Of course, because you somehow need to interface your Coq code, your C code, your Haskell. That project has some bits of Haskell code. We don't have yet the whole stack, right? So you have to like stop at some point, and you have to trust some things. And of course, from time to time, people discover bugs in those parts you trust, but you did not cover with extensive testing or proofs, right? Also, compser, the compiler, the C compiler. People also use fuzzy testing to find bugs, like in parser. There was a time when compser didn't have verified parser, and so people, well, yeah, okay, we can break this. And then, of course, the authors would come up and say, okay, but that's not really exactly fair, right? Because it's not the verified part. Okay, then there is a tool called QuickCheck, right? Of course, it's based on QuickCheck. It shows that it's amazing how it's applicable. I mean, this randomized testing, and so it's not tests or types, right? It's both. Like, let's take everything what is best from both worlds, right? So this is some stats on this verified file system project. So it's about 8,100 lines of, 81,000 lines of Coq code, right? And of course, if there are some parts, especially C parts, right, you can expect some mistakes in there. This is some stats for CompCert, the certified C compiler. And as far as I know, some people like who needs very high assurance in their software systems, they use this compiler in embedded systems, for example. So this is a pretty impressive project as well. So now let's turn to the theory part, the theoretic part. Okay, it's based on calculus of inductive constructions. So then this is based on lambda calculus, but with very, very expressive types. And you can, of course, it's not that you have only some basic types and like product type, arrow type, and you can combine stuff, right? No, it's in like open universe. You can add new types, right? As like data, the keyword in Haskell. You can create new types. And so this is based on dependent types and Curry-Howard correspondence, or sometimes people call it isomorphism instead of correspondence. So what's the main idea? By the way, who has heard and like has pretty good grasp on this part, like Curry-Howard correspondence? Okay, all right, that's cool. So I was actually afraid that I was gonna explain it to people who already know about this, and I would feel like awkward. All right, so the main idea is that propositions are special case of types. It's a special case of types. So that's why I didn't call it isomorphism. So isomorphism is one-to-one correspondence, right? But here I'm saying that propositions like a smaller, it's a subset, right? In a sense. And the proof is a program. So actually programmers are mathematicians already. You've been doing it your whole life, especially if you program in a language like Haskell. You just didn't recognize it. So if you know how to create a new data type with constructors, that's all you need. That's mathematics. You've been doing mathematics. You've been doing proofs. But you need a bit more expressive type system to do that easily, because in modern Haskell you can do dependent types. You can emulate them using like singleton types, for example. So what we have in Coq is we have one language in which you would write specifications, specs, and proofs. So you write programs, you write types, and there is no difference between programs and types, basically. Well, there is actually, but for example, there is no this distinction as in Haskell. In Haskell, the term language, the program language, and the type language, they are not the same at all, right? They live in different universes. You can reuse names, like you can say list or something like this, right? In Coq, you cannot do that because it lives on the same level, and that makes a very big difference. And so, since propositions and types, they're kind of the same, that means the type checking is your proof checking. You have a proof is a program. You've been programming for, I guess, a long time, right? You've been writing programs. That means you've been writing proofs, actually. And proving is programming. It's the same thing. That's the beauty of it. That's what I like about it. So what it gives you? It gives you high confidence in your code, right? Because if you write strong specs, then you're fine. You will get programs that are guaranteed to be correct. Of course, you would need some work to do, right? So you actually need to come up with the correct spec. So we kind of shift our trust to that level. If you do not write the right spec, the spec which does not correspond to the reality, right, as we see it, then it's not gonna get you anything good, right? So, for example, sometimes it's even hard to come up with a spec. Like, take a browser. What would be a spec for a browser? I have no idea how to specify a browser. I mean, if you try to do it, it will be very, very complex, right? And specs, they should be readable. So this is a challenge. But with this challenge, when you can solve it, it's very satisfying. Like when you type in Calc QED, Quadra Demonstratum, that's wow, it works. And ooh, you get like a shot of endorphins. Alright, dependent types. That's it. That's the only thing you need to know to really understand dependent types. Yeah, it's very simple, very easy. So you just need to like appreciate this simplicity. That's all. So this is a type. It's an array of some size, or sometimes people call it vector, for example. So your program will be checked that if you say, I want array of size n as your input, then your type checker would tell you, okay, you're trying to pass like array of size 0 instead of size 10, or you're trying to pass array of size n plus 1 instead of array n. And this will be caught at compile time, right? It won't leak into production. It's not gonna happen. So this kind of simple idea, it has some profound implications. You can do mathematics in Coq just because of this. So let's do a bit of mathematics. A very, very simple thing. But let's, take a step back and look at piano numbers. Piano numbers or unary numbers. It's a very simple thing, right? You remember something like Lost or whatnot, like the movies where like a bunch of guys are on an uninhabited island, right? And how do you count your days you spend there? You just put sticks, right? Then maybe you just cross, maybe you don't care about this crossing, right? It's like a hack. So you just continue putting those little sticks. And so this O, it's like stands for 0, right? It's resembles 0. So this is like the place you start putting your sticks, small sticks, right? Small strokes. And this S, you can apply it to a natural number, right? So S means successor, the next one. So you start from 0, you apply S, you get 1, you apply another S, you get 2, you apply another S, and so on and so forth. Simple, right? at this point. Okay, if you have a question, by the way, don't hesitate to ask. Yeah, if I'm saying something like not correct or vague or whatnot.
We'll check it with Cock.
Hmm?
We'll check it with Cock.
Sure. Okay, so this is very simple, right? You get two constructors. So you can define a list, right, in Haskell. You need two constructors, nil and cons. Here is basically a list of unit type. So you can define a list of a, list of integer, list of something, right? You can define a list of unit type, like parents, right? It doesn't mean anything, right? It doesn't convey any information, the unit type. It's sometimes it's used to defer computation if you are not programming in a lazy language, right? So you can actually see this is basically nil, and this one is tail, right? And we don't keep head in here. I hope I'm not confusing you right now. So natural numbers are basically lists where you don't keep any information. So cons of nothing, basically. So using the same technique, you can define what it means for a number to be even. This is a pseudo syntax. In real calc code, you would need to put a bit more stuff. I just kept it so not to confuse people. Okay, this inductive, yeah, I should have explained. Inductive, it's like basically data. It's an inductive data type. The same thing as data in Haskell. So what it means for number to be even. You can have a proof. This is called proof, right? So for natural numbers, it doesn't make sense to call these proofs. The constructors are not proofs every time, right? That's why I'm not saying it's not isomorphism, it's correspondence, because natural numbers, they are not proofs, but these are proofs. That's because I'm ascribing some sense to them, right? So you need to kind of get the sense. Okay, this thing, if you have if 0, it means you have a proof that 0 is even number, and it's a trivial proof, right? 0 is even by definition, basically, right? You can certainly divide it by 2. Now, if we have an even number n, from that we can prove that the 1 plus 1, or n plus 2, basically this, you remember that s means plus 1. So n plus 1 is also even, right? So if you have 0 is an even number, then applying this constructor to this proof, you would get that 2 is an even number. Or if you apply this constructor to this base constructor, right? It's also, it looks like natural numbers a bit, right? But these are type families, right? Sort of. If you apply those constructors to this kind of nil equivalent, you would get a proof that that 6 is an even number. So and by employing even more complex types, you could encode any mathematical proposition, and you can state anything, right? You can prove if it's probable, of course, right? If it's a correct statement, you can prove you build a program. This is a program, right? It's a term. Terms, programs, the same thing, right? You can build a program, and type checker will check that indeed this is a proof that 6 is an even number. So that's it. It's so simple that it might even, go unnoticed and maybe seem hard at first, but let me give some more examples. So for example, if you have some simple types, those can encode propositional logic, like very, very simple logic, right? So for example, if you have empty type, and empty type doesn't have any constructor, so that's why it's empty here. There is no way to construct empty type. It's like data, empty, that's it. No constructors. No way you can construct it. That would be corresponding to contradiction, right? To logical contradiction. Because if you can construct an instance of empty type, that means something is not consistent in there. You shouldn't be able ever build it, right? Okay, then we have unit type. In Haskell, it's just a pair of parens. That's a trivially true proposition, right? It's a proposition you don't really have to prove. You just say, okay, I have, it's called inhabitant. I have basically a term of this type. And then Haskell is confusingly the same, right? It's a pair of these parens, double colon, and again the same thing, right? I mean, syntactically. Now then, you can have a product type. It's like two things taken together. That's logical conjunction. You just say, okay, I have proof of this and proof of that, proof of two things. And I will show you an example with this. You can have a disjunction, or, right? You can have either this thing, left, or this thing, right. I mean, the Haskell constructors. Or you can have a function type, A arrow B, which corresponds to logical implication. Why? Because we're talking about constructive logic here. And constructive logic, which is for many people is different from classical logic because it doesn't have this thing which is called the law of excluded middle. So in classical logic there's this thing, either P or not P. Some of those is true, right? In constructive logic it's not the case, because in constructive logic you have to prove exactly which one is the case. It's either P or not P. In classical logic, it's possible to bypass this. It's possible to actually give a direct proof, okay, I know that some proposition P holds or it doesn't hold, or you can use the proof by contradiction, right? You can assume something. Like you can assume that something is not true, then you would prove that it's contradictory. And from that you know that, okay, so not P is not true, so that means not P is true. And in classical logic you can just keep this not, right? But not in constructivistic logic. So, okay, sure.
I was just thinking, why would you want a proposition that means contradiction? You cannot use contradiction as a way of proving things.
That's a good question. That's because you want to say something when something is not true, for example. And one way to do it is say, if I suppose that this is true, I get contradiction.
So that's by contradiction.
No, it's not the same actually. There is proof of negation and proof by contradiction. So proof by negation, it's admissible. Yeah, you can assume P, prove that it's contradictory, you get proof of not P. Or you can assume not P, prove that it is contradictory, get not P, and like scratch this double negation, right? Which is not admissible here. And so in constructive logic, proofs are actually programs, right? And so this function from proof of A provides a proof of B, which is implication. This is how implication works. And so let's do a simple proof. This is conjunction, but I use this star here instead of some fancy logical symbol, right? This hat or house, I don't know. So we're proving that if you have A and B, if A and B is true, then B and A is true. Like, very simple, right? Trivial. But you've been doing that in Haskell like all the time. It's very easy to write a function which actually does that. It's basically swap. You get a pair of A and B, and you swap it and you return a new pair of B and A. And this is a proof of this. So that's a very simple idea, and this shows on this like simple fragment of logic that yes, it works. You can prove that this is true, the statement to the right of the column, and its proof is this lambda term. This fun in calc means slash in Haskell, basically lambda, right? So if you take very big cock development, and you get this last, like the most important theorem, and you say print, it will just print you a huge lambda term. That's it. That's all. And that's mathematics, that's programming, that's the same thing. But it's not like that simple, right? We need for all and exist. If you want to do mathematics, if you want to, but why do you want to do mathematics? Because if you want to prove that your program is correct, like take some type class laws, right? People, the Haskell people like to write those out, right, and check them. So those are actually usually universally quantified. It might not be explicit, right? They might skip just as I did some slides ago. But we need those, right? Like for all inputs, you want, for example, if you have a function that sorts lists, you would need to say, okay, this function takes a list and returns a sorted list. It's a weak spec because it's not only sorted. It should be the permutation of the original one, right? Because you can return just basically any sorted list if you, let's say, sorting lists of integers, right? Okay, so for that we need two more types. It's called dependent function type and dependent sum type. There are also different names for these, and I find them really confusing, so I won't be mentioning them. And so what is dependent function type? It's basically like the arrow type. So if you squint hard enough, you would see that this is from A to B, kind of. But usual functions from A to B, you are not allowed to name the input argument in the type. So this is the type, right? Because we're in Curry-Howard correspondence, and types correspond to propositions, right? Or propositions correspond to types. So the thing is, this is very important. You are allowed to name your argument of your function, right? So this is a function from A to B, actually to family of types B, because now you suddenly you're able to parameterize your output type. And so, for example, you can say, okay, this function, let's call repeat, right? Which takes a number and an element and repeats it n times, right? It produces a list of n elements. You can actually have a type that would say, okay, this function returns the list of size n, where n is the input number, right? It's, if you go back several slides and remember that array n slide, that's it. So you need to be able to mention the name of the input argument in your output type. So this is a very profound change in type system, and it allows you to express many more things than if you didn't have it. Okay, so these are just functions. It's just lambda, blah blah blah, right? Now, dependent sum type. Okay, now I put a little bit more of calc syntax in there. This is existential quantifier, and it's existential type, right? If you're familiar with some advanced type systems, it's basically existential types. It is a pair which hides this like first component, right? So it's does it work? Okay, so exists, it's a type parameterized by two variables, right? One a is a type, sum type. It's like small letters in Haskell. Like you say square brackets a, right? It's like lists of type A, and so it's the same thing, but it's just customary in calc to name in the types like this: A, B, C, and so on and so forth. So this P is a predicate, right? So you have a logical predicate defined. So you can see it's from A, and it gives you a proposition, right? Predicates basically like functions from something to propositions. And how do you prove that something exists? And what this means actually, exists type. It means you have a predicate P, and you want to prove that there is actually a real element X which satisfies this property P. P is a property, right? Some specification. over x's. And so this type constructs, this mk exists as a constructor. Then you can ignore for all for a minute, and this is just a first component, x of type A, it's the first component, and p of x is the second component. And two of these taken together, like a pair, it's also called dependent pair. Together, they produce this type. So this type kind of hides the exact value of x. You're not allowed to learn it. You know that it exists, it's somewhere there, right? But you cannot unpack and look at it, as opposed to real pairs, right? Like ordinary pairs, where you can just unpack and see what's inside, right? So whenever you are handed with this exist AP thing, it means that there is an element satisfying property P. That's all you want to know, sometimes. In mathematics, it's oftentimes that's all you want to know. You don't care about the exact x. Probably you need to only know that it exists. Okay, that was probably the hardest part of the talk. Okay, so Coq is a programming language. What is it? It's a functional. It's dependently typed, so independently typed in the sense that I just tried to explain. It's also a total language. Total means every program has to terminate. You cannot write programs that do not terminate. It's not allowed at all. Of course, I would mention that you need your programs to terminate under some evaluation strategy. So actually, it's like it's called weak normalization. So maybe if you apply some strategy, like the eager strategy, right? If you immediately evaluate everything, then it might not terminate, indeed. But if you use something like call by need or kind of like lazy things, right, then it's guaranteed to terminate all the time. And of course, it's harder to program in a total language. Basically, oftentimes the totality checker, because there is not only type checker, but there is a totality checker. The totality checker would complain and say, okay, I do not see that it is terminating. And you're saying, indeed, it is terminating. I just don't know how to explain it to you. And you think of tricks, and there are some tools which allow you to deal with this. And it's a bit of a problem. But it turns out that, yeah, many of those things are terminating. You're not like writing non-terminating function on purpose of course, for server, they are not terminating, right? It's called conduction, but we're not touching it today. But sometimes, like if if you want to reverse a list, let's say, you're not supposed to write a non-terminating program, right? Like who would want to write a program which does not reverse a list, if it is supposed to? So now then, you cannot directly, as of now, you cannot directly run Coq. So if you wrote a program in a file, the file with this V extension, you cannot like compile it to assembly or to C. Well, actually, you can compile it to C. There is no compiler to do that, so there is extraction mechanism in place of it. What is extraction? It's basically like a transpiler, right, or compiler from one language to another. You can compile it from Coq into OCaml or to Haskell or to Scheme, or as I recently learned, to C. So a very interesting project that I didn't really have time to look inside. But apparently, yeah, there is. I'm not sure how stable this is. So of all these, OCaml works the best. But if you don't program in OCaml, it shouldn't be really a problem, because the language is clean and easy. And of course, you're not supposed to do much stuff in OCaml, right? Maybe you would need some glue code, but it shouldn't be too hard. Then there is Haskell extraction, and some people report interesting results using it. As far as I know, it doesn't work as good as OCaml, sadly. Sorry. Okay, so the Scheme one, it's this Lisp language, like Lisp family language scheme. Well, I think it's sort of abandoned. It works, but I'm not sure about like the quality, right? Now, what's this? Who knows what this is? I mean, don't try to read the text just like from the look of it. It's a hint. It has to do with Haskell. Hmm? Xmonad, exactly. Yes, it's Xmonad. Yes, it's a tiling manager, window manager. Yeah, usually it should be like a dark theme, right? But dark themes do not look very good on projectors, right? And so this thing is very famous. It's written in Haskell, one of the famous Haskell projects. So it turns out that this guy, Wouter Sweerstra, I'm not sure if I pronounced his name correctly, he ported Xmonad to Coq basically. So he would write everything in Coq and then extract it into Haskell and then compile Haskell, run all the tests. I forgot if he actually ran it on his machine or her machine. So it was kind of a long time ago, but it shows it's possible, right? There is lots of room for improvement because he was extracting it in Haskell. It's not that very well supported as OCaml. Now, what Haskell has to do with Coq? Let me highlight several, like 3 projects, right? 3 projects more, as opposed to Xmonad and Coq. So there is a HS to Coq, Haskell to Coq converter. It's a research project, so it's some people, Joachim Breitner, I think he's famous in the Coq community. They in this research group in the US, and Stephanie Weirick, and so they were developing this tool, and I guess Steve Danevich was also involved. Maybe he's like one of the main authors. And there is this group also involved in this deep spec project, Haskell plus core spec. I will shortly introduce a bit more about those projects. And also there is a library which is supposed to help Haskell programmers to get in touch with Coq and try and like make this transition if you want to take it a bit smoother. So what about Haskell to Coq converter? There is a paper called Ready Set Verify, which I enjoyed reading. I highly recommend it. I will give some links. It's in the slides, and I will make it available, and I will post a link in this meetup page. So they tried this tool, HS2Coq, on the containers library, which is known as a very well designed and very well tested piece of Haskell software. It's about sets, well, containers, right? So they ported this, well, it's like not ported by hand, they ported using this tool from Haskell into Coq. They wrote many proofs, and as their report goes, they actually added like 90% more code. It's only proofs, mostly. So yes, it can be time consuming, of course. It's probably the hardest part. So just write your program and hope it works is one thing, but to actually make this computer system believe it and make you believe it and the others, it's a bit more work, many more work, much more work. So of course there was challenge, partiality, right? So I mentioned that Coq is a total language. Every program has to terminate, and it sort of has to have this proof that it terminates. So you have to basically organize your code in a way that it terminates. And in those libraries, in the library, in containers library, there are some places where it's for a human being, it's kind of obvious that it would terminate if run, right? But for the computer, it's not so obvious, and this is a challenge. Sure.
So let me. I'm trying to understand exactly what you do when you say you are verifying the library. So as I understand, you take the library, the implementation of the library,
Yeah, Haskell code.
you put it into code,
Yeah, using that tool. Yeah, you translate. Yeah.
translate into code, and then you have basically all those types and all those functions that you, all the code that you have
Yes.
from that. Now, I mean that library already works.
Yes.
So you have some, I mean those functions that you had that implemented all those things translate into proofs that prove those types. That prove those propositions, isn't it? And then
So you
they're
actually,
proven.
that's a good point. You actually have to write your propositions, like mostly by hand.
So what do? You refine the types so the specification is more restrictive, or what exactly do you do to say
Yes,
it's
this is.
proven? Now I'm confident that it works as it's supposed to work.
Yeah, I was meaning to maybe show it interactively, but let me answer your question. So the thing is, in Coq, you're allowed, and maybe, yeah, in all the other systems, like interactive theory improvers, you're allowed to write your function for simple types, and later on prove a lemma about it. So you would formulate a statement like, okay, this is a reverse function. You can formulate a statement that it's actually reversing your list, for example. Or you can say, if you hit reverse some list, you will get the same list in return. So you can formulate these things, and you can. Yes, yes. It's a proposition then where this all this hackery comes in, right? You sit down and you write proof and you apply some tactics and whatnot. So yeah. So when they imported that, they had to add like 10 times more code to actually verify it. So they took a very well-tested library, and it's a mature library, right? And so it turns out that they didn't find bugs. Oftentimes you would find bugs. In this case, well, they found I guess they found a bug in tests. So something, yeah, small thing that they squashed, right? And also they are claiming that they learned a lot, and also the point of this, I mean, why would you take a mature library? You would need to test your tool first, right? And so this is a research tool. It's not like production ready, I guess. And so that's why they took that one. And also the library that they were testing, they were verifying, is a library that a lot of people rely on. It never hurts to actually get some more guarantees about that. Now we know that it's bugless, basically. That's all. And some people they gotta do it, right? Somebody has to do it. So I'm not claiming that every piece of software should be formalized. I mean that some critical pieces of software they should be. Like you would like your operating system kernel probably to be formalized, at least some critical parts of it. I don't know, maybe pacemaker, which works in a heart of a patient, right? If you, well, I'm not saying that you would, but if you're gonna get it, you would like to know that software there is impeccable, right? It works, and there is a specification, lots of smart people, and I don't know, take some other critical infrastructure that we have, like all those atomic electrical stations and stuff like that, right? You would certainly, you don't want very simple code made like in a day to work there.
But basically, when you verify, the only thing you're saying is that, that spec is, it works according to that spec.
Yes.
That spec is, it's expressed in a very complex language. The gap between that spec and what you really intended, that's where the problem might lie, no?
Yeah, there can be a problem. It can be hard to come up with a spec, but oftentimes it's easy.
That spec is almost as complex as the program itself. So
No, that shouldn't be like this. Yes, if you're writing a spec that is more complex than your program,
okay, I trust that the
that
program works according to this spec, but how do I track?
sometimes
This spec?
sometimes what you just mentioned, sometimes people actually do that. Like you can I don't know what to say, like let's take some the power function, like you can make a very slow power function which would just multiply like x to the n, right? x times x times x times x. It's very slow, right? There is a better algorithm, like a logarithmic number of steps, right? You can actually write your slow function first. It's very obvious that it works. It can be your spec. Then you write a very performant one, and you show that for each input, the output will be the same, and that will be your spec. It's totally legitimate to do that, and people do that. You have your golden reference, right? And then you have your complex, very optimized, highly optimized stuff.
In the end, it's like your executable code is one of the specs. In the end, just one spec, and you add more to the code.
It can be, yeah. Executable code can serve as a spec. Yes, that's correct.
So it's a kind of a spec.
Yes.
You define how.
Yes. Exactly. Yeah, the spec should be. You're absolutely right. The spec should be simpler than the code, right? Otherwise, there's no point. So if you cannot come up with a simple spec, then you should. Maybe your problem is not that doesn't have this good spec, right? Maybe you just didn't think hard enough. It happens. It's an art. Coming up with a spec, it's an art.
I mean, I can imagine like formal enough spec for real life problems, but I really struggle with the concept of backless software. I mean, that goes against everything I know. It's like you're telling me that I can be sure that some software is completely free of bugs, and that's hard to believe. That's like
yeah, don't take my words like literally.
No. I know that you're doing like formal verification rather than implementation. But, I mean, still it's a very, I don't know, foreign concept. It's something, I mean, that you are really sure that there is no bug in there. It's like.
I agree. Maybe you should just try. You know, it's very addictive. Okay, can we move on? Right? Yeah. So now this spec project, one part of it. So we were talking about that scary-looking hairy diagram, right? And another part of it is core spec. So basically, people, the same group, they formalize the core language of Haskell, right? Which it is compiled into, right? And so they have proven that the type soundness of this formal calculus, for the core calculus, right? And also they prove that it's compatible with extensions of Haskell, such as dependent types. And you might know that there is a project to bring dependent types to Haskell as well. But it's not going to be the same thing as in Coq. It's a different kind of dependent types. They made a different kind of trade-off. Because of all this Haskell baggage, basically, right? You have to take into account the context in which you do that. You cannot like redesign the language completely, right? Just to add an extension. And also, I'm not sure, but it looks like Haskell is going to land linear types, right? Which is also a cool concept. And it's dependent types, linear types. Nobody knows how to bring them together at this point. It's an open research question, and people are working on that, and it's a very hard problem. So we will see what happens. So there is a PhD thesis by Richard Eisenberg who introduced dependent types to Haskell. And so it's a very readable, actually. I highly recommend that. I didn't put it into the links, but it's a very cool reading. Also, there is a Haskell library written by John Wigley. He's a very famous Emaxer and very famous in the Coq community as well. Okay, so he tries to alleviate the pain for a Haskell programmer to get into this world, sort of. So you might want to try that out if you decide to actually try Coq, right? Now there is. Sorry, yeah, I should have mentioned that. It's the language of Coq. It has actually several, layers. So Galina, it means chicken, right? Coq means rooster. So it's basically this fun. When you have lambdas, it's called Galina. And also there is a language called vernacular. So if you see this inductive, it starts always with capital letter. It's like meta level, right? You define new data types and stuff like that. And Galina is just your proof terms, your specs. This is all Galina. And there is also LTAC. L stands for language, and TAC stands for tactic, because Coq is famous for using tactics to generate proofs, basically, right? So instead of doing them by hand, you can do amazing things with those. So there is also Coq equations plugin developed by Mathieu Souzon. This kind of looks like Haskell. I'm sorry, this the line breakage is not very good. So you say this is piece of vernacular. It's not standard Coq. You have to install a plugin. Well, it's very easy. It's on OPAM. You say OPAM install Coq equations. Boom. That's it. So this looks very much like Haskell, right? Except maybe for this because of some problems with notations. So this is basically like colon, the Haskell colon, but written as prefix, not as infix notation, right? So this is like pattern matching in place, and that's it. This is like fold function from Haskell, right? I think it should be easily recognized. Modulo some syntactic differences, and also this is a important thing, that in Haskell you wouldn't be mentioning these here, right? You would just say A, B, B, and so on and so forth, right? And instead of list you would say square brackets. So in Haskell you have implicit quantifiers. So here it means actually like for all, like for any alpha and beta, any function from L and so on and so forth. So Coq requires explicit mentioning of the types, basically, like all the parameters. But since I put those into parens, it means they are implicit. So if you skip them, Coq will be able to infer. So you see, this part does not mention these arguments. These are real arguments. So how does it work? When you supply function f of type alpha, beta, beta, Coq immediately says, okay, this is alpha, this is beta, I know what my implicit arguments are. So it has an unification engine, it can infer stuff for you, and people actually use it to a great extent. So you can even prove some basically theorems with this unification engine. It's called lemma overloading, and it's a very cool, mind-blowing stuff that you can program in this way. It's logical programming basically, but on this level. So it's very much different than LTAC. So some books and blog post papers that I would recommend if I manage to sparkle some interest in you. So there is the Software Foundation series. It's a series of books by Benjamin Pierce, the author of TAPL, Types and Programming Languages. It's a very well written book. I mean, especially the first one, for example, it gives you like a really gentle introduction into this area. They are specializing in types programming languages, right? So it means that you will be seeing lots of programming languages theory. If you're not interested in that, you can read probably like the first half of the book, and it's interactive. You download it, you fire up an IDE-like thing, like Emacs or Coq IDE. You go through the text. It will offer you explanations, examples, exercises, and you do exercise exactly in this environment, right? So oftentimes you will be offered to prove some theorem. You prove it, you don't need a professor to check. You have this system working free of charge, like you pay for electricity. Okay, so then there is this book by Programs and Proofs by Ilya Sergey. He used to work at MDI Software as well for like 3 years, I guess. He then moved to UK. And some blog posts and papers. So Joachim Breitner, he was doing this thing, and he is doing a great job at explaining how to use Coq for Haskell programmers. So he's like into this intersection of these things, right? So then there is this blog post which I enjoyed, Haskell for Coq programmers. So it's like from the other side, right? And if you know Haskell, it is worth to read this. And also this paper, Ready Set Verify, it's where they did this stuff with the containers library. It's very well written. It's available on archive. Questions? Do we have any questions? I know that we had a lot of them. Well, maybe not a lot, but some of them during the talk. It took longer than I would expect. Okay.
Is this somehow applicable to other languages? So is there a way to prove things written in other languages by using any of these techniques, or
Well, in principle, you can take the same approach like HS to code. You can have Ruby to code, basically. And I think that some Japanese guys, they did that. There is a work. This guy. Let me show this one. So check out this one and links from this repo. And I think you should be able to find this Ruby thing. But the talk was in Japanese. So I just, like fast forward in YouTube and just looked at the slides. That's all what I could do.
but I guess that there might be some requirements for the language. I mean, it should be the same type or something.
But
I can hardly imagine Python to go for something like that.
I mean, you certainly can do something about that. It's a thing that I just stumbled upon when I was preparing the slides, so I didn't go into that. Yeah, it's. I was amazed actually that okay, for Ruby you can have that one. So yeah, that's cool. People are doing that. Okay.
Says that every program has to terminate.
Yes.
But isn't termination a unstable problem? So how do you assure
Yeah, you wouldn't be able to prove that every program terminates, of course. Yes, but the programs you write, they terminate, right? Most, mostly. And if they don't, it's a mistake, right?
the termination checker can protect everything?
Yes, it's not always very easy to work with this. You have to sometimes work hard to actually explain to it that it actually terminates. It's sometimes not really easy. So the thing is, how does it check? It uses very simple syntactic approach. If you call yourself recursively on strict subterm, like if you had a const, you call yourself on tail, right? Or maybe it can allow you some shortcuts, and if you call it not on tail but on tail of tail, something like this, right? And so in this case, yes, it knows it will terminate, right? But sometimes, so for example, let's say the conjecture when you, if you have an even number, you divide by 2, right? If you get in the process an odd number, you do times 3 plus 1, right? How it's called? The conjecture that it always terminates. Collet conjecture, yes, thank you. Yes, so you wouldn't be able to write it like this. Well, if you can refactor it, then you have a proof that it terminates always, and that's a very cool thing, right? You can go for this. Yeah, you can get a prize, whatnot, right? That's very cool. But yeah, Coq allows you to write non-terminating programs. It's called k-induction. You can do it, for example, if you want to write a formalized, let's say, a web server. And actually, people have done that. They formalize all sorts of stuff. There is a, I'm not allowed, I guess, to pronounce this. It's like P browser for watching. Okay, so they formalize even that. So people formalize lots of things. It's amazing. And yeah, going back to co-induction, you can have things that do not terminate and they are productive. You can prove that some things are productive. Every request will be served and so on and so forth. It will be going on and on forever. So you can have that sort of program, which is always productive, or a program that always terminates. You cannot have like lists in Haskell. Lists in Haskell are kind of weird, sorry. So on one hand, they are lazy, so they like in infinite, right? and on the other hand, they can be finite. In Coq, they are either finite or infinite, either streams or lists, not like at the same time both. And so yes, it can catch you, and if you introduce some non-termination, or you cannot, for example, you cannot skip a case in match, right? In match construction.
I was working with Coq a few months, and I find it very complicated, this separation between tactics and the language of definition. So my question is, from a Haskell perspective, why is better to learn Coq instead of Agda, where the syntax is more close to
Yeah, the thing is, yes, thanks for the question. Yeah, it's a good question, actually. I would answer like this. There are very big projects in Coq, very, very big and famous theorems, and even real compilers for C, for example, formalized. There is infrastructure. Yes, I agree that tactics are confusing to work with. That's why we almost never use those, because we use a great library, MathComp, and it allows you to skip all this LTAC hackery. Maybe not all of this, but almost, right? And in Agda, sometimes it takes very, very, it's a hard effort to write something really, really big with lots of cases. You have to think hard about that. You have to refactor your development. So, for example, in programming languages theory, it's often the case that you have lots of cases. Like you have lots of different types of kinds of expressions, for example, right? And sometimes you have statements about pairs of expressions, like this program steps into this program, for example, this stepping relation, right? And so when you try to prove stuff about this, you would be dealing with pairs, and pairs give you like quadratic number of subcases, right? If you had like a language with 50 constructions, when you are talking about pairs, you will be dealing with 2,500 constructions, and you have to be clever how to actually not overdo these things. It can become hard to manage. But of course, Agda is really cool, and I don't know it really well. I have experience, and I usually, except for Coq, I program in Idris, and these are very, very similar things. It's really hard to do these, like big developments for me. Maybe I don't have enough experience with this. On aesthetics, like the aesthetics of dependent types, yeah, it's better, I would say. But the thing is, when you employ dependent types from the very beginning, you kind of like you cannot go back. So once you written a program with this spec using dependent types, you have to constantly prove stuff about it. When you use this function, you have to say, okay, yes, I'm using it on the subset of inputs it is supposed to be used, and so on and so forth. In Coq, people usually program with simple types. Like, I have this list, I produce this list, right? No type structure. And then later, you add lemmas about it. And so you can program like a OCaml or Haskell programmer, and then later formalize things that you want to be sure in, right? And so I think this is easier. And so, for example, okay, let's say you formalize stuff with dependent types from the very beginning. So if you have a function that source list, you just express it in its type. Then what if you want something else? What if you want those lists to be always non-empty? You would have to go back and change everything, right? But in this case, you can add more lemmas. That's all. So I'd say, yeah, it's there are upsides, downsides to each of these systems. Yeah. And if you're like want to use it in practice, I think Coq is more mature system, probably because like Agda is 10 years old, right? Coq is much more mature in this case. Uh,
by the author
y-
within
you mean do you mean this slide?
software foundation.
Yeah, the Software Foundation series. Yes, it's a freely available electronic book.
No, but
Okay.
I mean that there are also on YouTube, some videos on
Ah,
YouTube about the course that he gave, and he like goes
yes.
through the book really quickly, but just focuses on the essentials, which is quite nice. Instead of just reading the whole book, which is quite long.
Yeah, I highly recommend those. Yeah, there is Deep Spec YouTube channel. You can find Deep Spec Summer School, and those lectures are very good and they're accessible. Also, if you want to, double your feet into that, then feel free to check out Cox GitHub. It has lots of stuff in it, like where the community lives. There is a mailing list. There is a Slack channel. There is IRC channel. There is you can ask stuff on Stack Overflow. You can open issues. You can go to Gitter. So you can get help in any way you like. You would prefer, right?
The question is, why is there a prop type or a set type instead of the
Yeah, that's a difference also between Agda and Coq. That Coq is an so-called impredicative system. So they have this prop universe, which is useful, very, very useful for extraction. So prop is impredicative. What it means, if you have for all propositions and you state something, it also will be a proposition. So impredicative means you can like refer to everything else, including itself. This is impredicativity. And Agda is this is a predicative system. They like it, and they are trying to edit, right? So I have a coworker here with me. So Joachim, he works with Agda a lot, and so he told me that there is some ongoing effort with adding sort of impredicativity, right?
Yeah, I've heard that they are going to add something at all. Although I'm not sure that they are actually going to add imprecitivity. They might just add the prop universe instead.
I see. So yeah, this is like an issue of type theory. It's kind of very deep issue, and that's a very good question as well. And so, why is it useful for extraction? Whatever lives in prop cannot escape it. So if it's a proposition, it's only makes sense for the logical part of your development. So you cannot use things which are propositions to drive your computations. Like you cannot use a proposition to get a list. At least as I mean, it can be some trivial, right? Something trivial, but propositions cannot affect computations, and that allows you to erase those. That's another big problem with these dependent types. You need to, well, types need to be erased, right? They do not make sense at runtime, right? Well, sometimes they do, but I don't think it's a very good design. So you're supposed to get rid of the types, erase them completely. And so this thing, confining the logical part to prop, to this universe, which they cannot ever go outside, that's a good thing for extraction.